everyone. Welcome to episode number 681 of this here electronic engineering podcast called Amelia's Weekly Fish Fry, brought to you by eejournal.com and written, produced, and hosted by yours truly, Amelia Dalton. Today, we're diving deep into the world of RF system design. We're going to discuss why system integration has become the single highest risk phase in RF programs, and why traditional RF, EM, and signal processing tools just aren't cutting it when it comes to full system visibility. The solution? A new paradigm, the RF digital twin. My guest this week is Giorgia Zucchelli from MathWorks. Giorgia and I explore what an RF digital twin is, how it revolutionizes the design and validation workflow, and how AI is playing a critical role in its development. So, without further ado, please welcome Giorgia to Fish Fry. Hi, Giorgia. Thank you so much for joining me.
Thank you for having me.
Absolutely. Okay, so we're talking all about RF system design today. But first, Georgia, what do you think is driving the recent increase in complexity in RF system design?
Yeah, it's a huge trend, and it's really something that we are experiencing almost every day. The RF systems are no longer single purpose design, they are highly reconfigurable. Multi-mission platforms where essentially performance depends on tight interaction between the hardware, the digital signal processing, the algorithms, and as well the environment where they operate. There is also a major trend is pushing RF towards a higher and higher frequencies. So for communication, 5G and 6G, we are talking about FR3, that is around 10 gigahertz, let's say. More and more applications moving towards the millimeter wave range, 20, 30 gigahertz and up to the sub-terahertz range. So higher frequency, larger bandwidth, this also the trend of packing together more and more antennas. So we have highly reconfigurable systems, higher frequencies, larger bandwidth, more antennas. This means a lot of headaches for the system designers and the RF designers because these platforms are essentially very, very complex. So we're not talking anymore about RF components, but we're really talking about platforms. So beamforming platforms, active electronically scanned array, AESA. These are essentially systems that are very modular, programmable, reconfigurable, and they have thousands, if not millions, of possible states. So typical designs, they are made of tiles that can be combined so that they can really extend the size of the phased array depending on the application that designers are looking at. So we see, for example, the same platform that can be repurposed from radars to satellite communication systems. So this is amazing because essentially the system integrators, whether they are the builders of radar systems or payload or satellite systems or base stations, they can use this architecture and they can be retargeted through software to support multiple modes, multiple communication standards, multiple operating environments. So it's one hardware to serve them all. So this hardware flexibility really enables a faster time to market, multi-mission systems, great, simpler life cycles for the products once they are deployed. However, there is the other side of the coin that this flexibility also makes design by prototyping practical. So back in the days, a lot of the RF designs were made mostly in the lab by tweaking and tuning and turning screws. Nowadays, because of this highly reconfigurable property of the system, design by prototype is not possible. So these parallel trends that really makes the life of system designers, I would say, interesting, if not complicated as well.
So, Georgia, why is system integration now the highest risk phase in RF programs?
Yeah, it's because I was saying these systems are highly reconfigurable at every level. The RF front end, the signal processing, the algorithms, and integration is where essentially everything comes together. And the first point where these cross-domain interactions become visible. So all those issues that do not appear or are not apparent in isolation, they unfortunately pop up once you connect the different parts of the system together. And essentially, because these systems are so highly reconfigurable, it's very, very hard to validate all possible operating modes, especially independently, because nothing is independent anymore. And one thing to keep in mind is that the human mind, when it comes to deal with such degree, or can I say, of reconfigurability and complexity, tends to make a lot of assumptions. So we make assumptions to simplify the design and make sure that we can cope with this complexity. And these assumptions that are in general made at design time break down when the real hardware is integrated and when it gets exercised in the operating environment. And of course, when you find an integration issue only at the integration stage, then it's often too late. So it becomes very, very expensive. Even just prototyping these systems is incredibly expensive. And these are a costly error and add a lot of risk to the success of the projects in general. And this is really where tools like MATLAB can help, because essentially by bringing the algorithms and the components or the impairments earlier together, you can hopefully find these problems and validate the assumptions as early as possible in the development cycle, well before prototyping.
So, Giorgia, why can't traditional RF, EM, and signal processing tools provide full system visibility?
Each of these tools are perfectly fine. And one thing that I like to say is that engineers do not fail because they don't have tools or they don't have the right tools. But they often fail because different tools, they don't talk to each other. I don't mean by simple API or programming interface. I really mean by in terms of abstraction level or in terms of functionality. So each of these tools, they do a very good job, but they often work in isolation. They maybe focus on component level or the domain-specific analysis rather than looking at end-to-end system behavior. So it's one of the reasons why these tools cannot capture cross-domain interactions between RF, digital signal processing, algorithm, and environment. But these interactions occur in the real world. So many workflows rely on data sheets or small signal assumptions. That's one of my favorite assumptions when dealing with RF systems. But they fail under mission conditions or when you analyze different reconfigurations of the hardware or when you take into account the different impairments. As architectures grow more and more adaptive and multi-mode, unfortunately, late integration problems become the critical items that, when become visible late, essentially drive up the cost and the risks of the project. One example that I like to bring is a satellite communication system where you have a large phased array on the Earth pointing up towards the satellites that are flying 500, 600 kilometers up in the sky. And the passage of a satellite just takes a couple of minutes at most. It's really, really fast. And then you have to point all these elements, thousands of elements, hundreds of elements of the antenna transmitters towards the satellite. Some of them will be in saturation, some of them will be in more linear conditions. So each of them essentially is independent and operates in different conditions. And that makes it extremely hard to analyze and to build robustly. So that's where really building models and performing system level analysis becomes really, really important.
So, Giorgia, what is an RF digital twin? And talk to me about how it can change the design and validation workflow.
Yes, exactly. That's exactly what I was pointing towards, that modeling and simulation helps in anticipating the impairments, in anticipating the problem. The digital twin is essentially a virtual representation of the hardware, but together with the system level context. So a digital twin is not a standalone component model and is not just a simple model. It really combines multiple abstraction levels. It can combine measurement data. It can combine behavioral models, physics-derived models into a single workflow. I like to think of a digital twin as a big container that builds really a digital thread that connects the requirements, the simulation, the measurement data as the project proceeds. So digital twins are more than just models. They really provide a companion to the hardware development and to the application development. I like to think that the digital twin helps in building applications such as satellite communication link using a specific hardware that is available, or on the contrary, helps designing hardware to serve a specific application. So the digital twin really provides the glue towards the system level and the component levels. That's the way I like to think about it.
Okay, so how do you think AI can help in the development of these RF digital twins?
AI can help in millions of ways, I would say. First of all, with the extraction of behavioral models from measurement data, with the analysis of measurement data or simulation data. Because these systems are so highly configurable, they are multi-mode, like I was saying before, multi-standard. They have thousands of different configurations. It goes by itself that when developing such an adaptive system, you drown in data. You have a lot of data, and it becomes really hard to analyze it and to make sense of this data. And if you like, to find the needle in the haystack. So AI really helps with this aspect, that is processing the data, understanding the data that is available, making sense of the data that is available, and eventually use this data to build better models, behavioral models, or higher fidelity models that really are faster to simulate and that provide meaningful results once integrated at the system level workflow. So AI, I see it in a very utilitarian way. AI automates the manual characterization workflows by making it more automatic, essentially. So it helps streamlining the tedious work that nobody likes doing it. It improves speed, repeatability, scalability. And by building neural networks that are dedicated to specific application, you really can close some specific gaps that are in traditional behavioral modeling techniques. One of my favorite examples is the use of a neural network for reconstructing the radiation pattern of antennas based on orthogonal cuts or partial data or partial measurement that is made available either through data sheets or through measurements. And layered on top of this, on these more traditional machine learning techniques, now we have all the agentic workflows. And agentic workflows really provide an enormous boost in productivity for the experienced designers, exactly for the reasons that I was describing before, that essentially you speed up the tedious work, you automate a lot of the boring work, you get inspiration and motivation to focus your energy on the most creative part of your work, and you let the agent do the boring part, if you like. So AI is a really fantastic companion to build complex models and complex digital twins of the complex platforms that we are seeing today for RF systems applications.
So, how do cross domain interactions in RF systems impact performance, power, and thermal behavior?
Yeah, so ideally an amplifier just amplifies the signal, a modulator just converts it in frequency, and the filter just filters it. In reality, there are impairments, and these impairments propagate upwards. And they affect system level performance that can be in terms of error vector magnitude or detection probability, essentially, link performance. So these are trade-offs that really require the designer to have an incredible mental agility in going all the way from the details of the component or subcomponents to understand what is the impact of these details and impairments at the system level. So there is the fundamental need of being able to trace back and understand the cause and effect. So you really need to have tools that allow you to essentially analyze and isolate different impairments and directly see the effect of these impairments at the system level. For example, some of the things that you can do only with simulation models is remove the noise from your system. You can say, now all my components do not generate noise. Is my system working, yes or no? And if your system is not working, then it means that the problem is most reasonably not caused by noise. So having this ability to to analyze different scenarios, to build different what if test cases is really essential for the designers to gain a better understanding of where things are working and where things are failing. So that is the way I think that why is it so important to build these digital twins to better isolate and understand these cross-domain interactions well before the system gets deployed in the field, so that you can really look at the different scenarios. One typical case is how does a mobile phone work once it's deployed in a stadium with thousands of other mobile phones operating in the same environment. These are things that are incredibly hard to test in real life, but become increasingly more possible to be studied with behavioral models and digital twins.
So, Georgia, your work in this area will be discussed at the upcoming IMS conference in Boston, which takes place June 7th through the 12th. So, what are you hoping engineers will take away from those sessions?
Yes, I'm very excited to come to Boston and participate to IMS. We have a lot of presentation and sessions. And the main message for me is really that I hope that engineers understand how system integration is now the highest risk and the phase of the design that requires the most attention and care from the system developer. It's not about optimizing a single component. Often case I see a ref designer spending an enormous amount of time in squeezing the last bit of performance out of a single amplifier or a single filter, when in the end, this optimization doesn't really lead to a better system level performance, maybe because the issues are elsewhere, or maybe because you can rely on digital signal processing algorithm to compensate for some of the impairments of these components that are far from ideals. So I really hope that people can take away that RF digital twins are the way forward, are the main tools that to enable engineers to connect the hardware behavior or the component behavior to the system level metrics to assess, for example, mission level performance really early in the design, really before the prototypes are made. So at IMS, MathWorks will have several workshops, presentations, demonstration at the booth, where we really want to bring practical examples of measurements validated workflows from antennas to RF components to algorithms, all connected together to build a system level perspective and a system level workflow for the system integrators and the developers of communication and radar systems. So I really hope that there is that will allow engineers to bring home when to use physics-based models, when to use AI-assisted models, or a hybrid of the different type of models, and how to deal with different level of abstraction, ranging from the simplest model to the most complex and sophisticated techniques. The bottom line is that depending on where you are at in your development cycle, where is essentially the pain that your system is experiencing, you might want to use different type of models to trade off fidelity and speed, essentially. So that's really the message that I hope attendees of IMS can take home.
Fantastic. Okay, Georgia, one last question before you go. If you could have one meal right now, it doesn't matter if it's on the other side of the world, you need a passport to get there, what would you have?
Ooh, I'm Italian, living in the Netherlands for now 20 years. So I miss a little bit of Italy, I can tell you sometimes. So I would have a total comfort food. I would have a flat bread from the region that I come from. It's called piadina. It's like a funky sandwich, let's say, just better. And this is what I was eating when I was a child. So brings me good memories. That's what I would go. Nothing fancy. It's funny. You find the fancy stuff all over the world, but the simplest food, the street food, is the hardest one to reproduce.
I agree. I love it. Well, Georgia, I think that's all I have time for today. Thank you so much for joining me.
Thank you. Thank you very much for having me on the podcast.
If you would like even more information about this topic, I've included a couple links below the player on this week's fish frying page on eejournal.com and in the description for this week's YouTube episode as well. Hey, have you checked out EE Journal on social media yet? Well, you should. You can find us at facebook.com/EEJournal. If LinkedIn is your thing, I dig it. You can follow us or me on LinkedIn, and we are also on Blue Sky Social and Mastodon as well. And we have a YouTube channel, youtube.com/EEJournal. Folks, it is chock full of all kinds of techie videos, including our very popular Chalk Talk webcast series, hosted by me. And of course, you can subscribe to our EE Journal YouTube channel as well. Thank you everyone for tuning in. If you know of any cool new technology or heck you just want to chat, shoot me a line at Amelia, that's Amelia, at eejournal.com, or post a comment on our forums on EE Journal. For the week of May 8th, 2026, I'm Amelia Dalton, and you've been fried.